Okay. As you can tell, it's Hawaiian shirt day in the physics department. It takes a certain something to pull off a Hawaiian shirt. I got it. Okay. Just have to look like you've been to a few luau's. Okay, we talked about angular velocity last day, and we found that it was defined very similar to linear velocity. Linear velocity is how far you get down the road in a second, and angular velocity was how far you got around the wheel in a second. And so when we looked at this sample problem, yes sir?
We were talking about how, like for distance, you can go there and back and your average velocity is 0 then. Let's say you're spinning one way and then revolve the opposite way. Does it cancel itself out in that case?
In that case they would, yeah. But I can't remember ever going there. Okay. In the case of a second hand on a wristwatch, it goes once around, or 2 pi radians, in 1 minute, 60 seconds. And so we take the 2 pi radians, we divide by 60 seconds, and we get about 1/10 of a radian per second. Now in your problem number 2, you were looking at the minute hand, which goes around once an hour. And in that case, you would divide the 2 pi not by 60 seconds, by 3,600 seconds. Now the direction of that in both cases, we want to say clockwise, but remember with these rotational problems, clockwise can be a problem. Sometimes we have to get on different sides of the problem. So instead, we use a vector. And that vector has a very odd direction that it's defined to be. We find that every part of the wheel changes direction as it turns, except the axis. And so, as strange as it seems, we define that to be the direction of our omega vector. It points out along that axis. Now, it turns out that there's 2 ways to point along an axis. I can point that way or that way, which is convenient because once I've defined an axis, let's say that's my axis, there's 2 ways to rotate about that axis. And so we assign one of those rotations this direction, we assign the other rotation the other direction. And we remember which is which by using what's called a right-hand rule. We curve the fingers in our right hand around the direction that it's rotating. Our thumb on our right hand reminds us which direction the omega vector points. If I had this going that way, I'd use my right hand and I'd get an omega vector that way. Now, if we go back to the problem with the wristwatch, the second hand and the minute hand are both going clockwise as viewed from this side of the watch. The best way to describe that direction would be with right-hand rule into the wrist. Now you can't really call that down unless your wrist is like that. If your wrist is like that, then it's going to be up, but it's always going to be into the wrist. Now let's look at that problem that you just voted, or you just turned in rather. If you have the Earth, and that Earth spins about some axis, and that would be Santa Claus's workshop there, and down here there would be penguins. Okay, and this whole thing would rotate like that. Now, if someone lives on the equator, and you live up here at Bozeman. You've got a big head. Both you and your friend are going once around every 24 hours. That's 84,600 seconds or something like that. I can't remember quite. It's a lot of seconds. Anyway, so you would both have the same omega. Every person on the planet has the same omega. We're all moving on the same wheel. And the direction of that omega has to point along this axis of rotation. It's either going to go up through Santa Claus's workshop or it's going to go down through the penguins. Tell your neighbor which it does. Santa Claus or penguins? Okay. Since we're always following Boston as the Earth turns, that omega vector is going to point up through Santa's workshop. Actually it goes right through his living room. Or we could say it points towards the North Star. Any way you'd like to describe that. Okay, new topic. I have this wheel, and I have it spinning very, very fast. And its omega vector, by right-hand rule, would be pointing towards the open door. And so I've drawn it here. It's long because that wheel is spinning fast. Now if I put my hand on the side of that and slow it down, well, the omega vector is still pointing towards the open door, but now it's shorter. Now the question is, how much did it change? Well, the change vector is what I have to add to the initial. There's the plus sign right there. What I have to add to the initial to turn it into the final omega. I'm trying to make a long vector short. I've got to add something in the opposite direction. Now, in the olden days, by that I mean the first part of the semester, we defined linear acceleration to be the change in the linear velocity that happened in 1 second. Well, now we're going to define something called angular acceleration. We use alpha to represent that. And that's just going to be how much the omega vector changes each second. Okay? Now, if we use that definition, we see that alpha always, every stinking time has to point in the same direction as the change in omega vector. Turn to your neighbor Nimrod and explain why that is so, and use the word DeLorean. DeLorean. Okay, talk to Nimrod. Talk to Nimrod. Okay. What you should have said to Nimrod is, unless you have a DeLorean and a flux capacitor, you cannot go backwards in time. That means delta t is always a positive quantity. Time marches forward. That means that this vector and this vector have to point in the same direction. The only way you can get a vector to point in a different direction by multiplication or division is if you multiply or divide by a negative number. If you have a vector due east and you multiply it by 2, it's still due east. It's just longer. Okay? Now, what this means is that whenever we're slowing a wheel down, whenever it's turning slower and slower, the omega vector and the alpha vector will have to be in opposite directions, as in this example here. If I'm speeding something up, so it's going faster and faster, the omega vector and the alpha vector will be in the same direction. Does this seem familiar? Have we been here before? Yeah, you're going down the road on a straight road. If you're hitting the gas and going faster and faster, velocity and acceleration are in the same direction. If you hit the brakes, they're in the opposite direction. Okay? Now, I want to caution you. The right-hand rule gives you the direction of the omega vector, period. Full stop. Nothing else. Okay? Some people learn that right-hand rule and they want to use it for everything on the final exam. They say omega's out of the page by right-hand rule. Alpha's into the page by right-hand rule. It's Tuesday by right-hand rule. Everything's right-hand rule. Right-hand rule only gives you omega. How do you get alpha? You ask yourself if it's spinning faster and faster or slower and slower. If it's faster and faster, it's the same as omega. Slower and slower, it's opposite. There is no right-hand rule for alpha. See if your neighbor understands that, please. Now, I'd like to convince you that where we're going is exactly where we've been. If I were to take a ball and throw it straight up at 20 meters per second, how many seconds before it stops at the top? Shout it out. 2. A mighty shout goes up in the land. Okay, 2. How do we know that? Because it starts with 20, and every second that goes by, we add 9.8, let's call it 10 meters per second down. Well, it's going to take us 2 seconds to whittle away at 20. Okay? Now, let's look at a different example. Suppose I have a wheel that is rotating like that, such that the omega vector, the red omega vector, is pointing by right-hand rule towards you. And it's slowing down so that the alpha is away from you. Now this didn't used to be cut off. It was nice and beautiful until we got a new version of PowerPoint. Bill Gates did that to me. You'd think a multi-million billionaire would have better things to do than pick on me, but there you go. Now, I'm not real good at drawing things in 3 dimensions like that, so I'm just going to take that wheel and make it flat on the page. But that means I'm going to need to represent vectors that are coming out of the page and vectors that are going into the page. Now there is an accepted way of doing that. A vector that's coming out of the page, we draw this way, and this represents the point of the arrow coming out towards you, straight out of the page. This vector is going into the page, away from you, and you see the feathers at the tail end of the arrow going away from you. Now suppose I told you that this wheel started with an omega that was 4 pi radians per second. Just as an aside, how many times is that going around each second?
2.
Twice, okay? If it has an alpha in the opposite direction, it's slowing down. If that alpha has a magnitude of pi radians per second every second, how many seconds before this wheel stops? Shout it out!
4.
4. All right, you got it. You got it. One more connection. This wheel of serious injury here. If I get it sped up here, so that its omega by right-hand rule is right out along that post. Well, this wheel is weighted so that it doesn't want to slow down. So the spin rate stays the same. Now the spin rate tells me how long the omega vector is. It's not speeding up, it's not slowing down. The omega vector is not getting longer, it's not getting shorter. It always points out along that bar. Is the omega vector changing?
Yes.
Yeah, it's changing direction. And because the omega vector is not getting longer and not getting shorter, the alpha cannot be along the direction of omega or opposite the direction of omega. The only direction left is perpendicular to omega. So I have a little representation here. Let me spin this up again. Again, if this were Harvard, we'd have a machine or a grad student to do that. Okay, so the omega vector is always pointing along the red arrow, and it never gets longer or shorter. The alpha vector is the blue arrow. It's always 90 degrees to the red arrow. What does this remind you of in the linear kinematics case? Talk to your neighbor. Talk to Nimrod. Okay. Brave soul, what does it remind you of? Raise your hand.
Centripetal acceleration.
Centripetal acceleration when you're going around in a circle. Okay? If you put cruise control on and you go around in a circle, you don't change the length of your velocity vector. But you are changing the direction of the velocity vector, and that means your acceleration vector has to point 90 degrees. Which in a circular case is towards the center, and hence we call it centripetal or center sequence. Okay, now here's the magic. Here's the big connection. The definition of linear velocity was how far we got down the road in a second. The definition of angular velocity is how far we get around the wheel in a second. And because those definitions all look so the same, they have the same relationships, we find that the kinematic equations look the same. The first kinematic equation looks like that. And you see, everywhere we have a linear velocity, we replace it with a rotational velocity. Wherever we have a linear acceleration, we replace it with an angular acceleration, and time is time. But all four of my kinematic equations have a rotational analog, and all I have to do is make the replacement between the linear, like in this case delta x, with the rotational delta theta. Now, we solve linear kinematic equations by making a list. We make a list of the 5 players and that list always looks the same. We've got delta x, we've got A, we've got B initial, B final, and delta t. And we have to find 3 of these from our problem statement in order to solve for the other 2. Well, in rotational kinematic problems, we have the same list, but with their analogs. Instead of delta x, we have delta theta. Instead of A, we have alpha. Instead of v, we have omega, initial and final, and time is time. And you have to find 3 of those from the problem statement. Here's a problem. The drill bit of a variable speed electric drill has a constant angular acceleration. That angular acceleration is 2.5 radians per second per second. The initial angular speed of the bit is 5 radians per second. After 4 seconds, what is the bit's angular speed and what angle has it gone through? See if you can solve this problem. I'll put up the equations up here. Okay, let's solve this together. I know that the angular acceleration is 2.5 radians per second every second. I know that the initial angular speed is 5 radians per second. And I know that we're looking at this thing for 4 seconds. In part A, we're looking for the final omega, and that makes this delta theta the who cares. Now, that means that I need the equation that doesn't have delta theta. I don't know delta theta, I don't want to know delta theta. I need to use the equation that doesn't have delta theta. Well, there's delta theta, there's delta theta, there's delta theta. I have to use this equation up here. So let's do that. So I say omega final is equal to omega initial plus how much the change I have per second times the number of seconds. So this is going to be 5 radians per second plus a change of 2.5 radians per second for each second times 4 seconds. That's going to be 5 radians per second plus another 10 radians per second during those 4 seconds, or 15 radians per second. Now, if I'm looking for the angle, I'm looking for delta theta. I plug in 15 radians per second, and now this goes from who cares to being worth $400,000. But because I have 4 pieces of information instead of 3, I can use more than one equation. Indeed, because I have all the other variables except for delta theta, I can use any of these equations that has delta theta in it. So I could use this equation to get my answer, this equation to get my answer, or this equation to get my answer. You might try using all 3 equations and make sure that you get the same answer in every case. You will, okay? Let's use this one here. Whenever I can, I try to use the top 2 equations because they're the ones that are actually the rewrites of the operational definitions of acceleration and average velocity. Okay, so let's use that second equation. I'm looking for the angle that this bit has moved through. That's going to be delta theta is equal to 1/2 omega initial plus omega final delta t. That's going to be 1/2 The initial was 5 radians per second. The final is 15. And the time is 4 seconds. 5 and 15 is 20. Half of that is 10. 10 times 4 is 40 radians. So it goes around about 6.5 times. A little more. Check that your neighbor's on the bus, people. Okay, now that you've seen me solve a problem, why don't you solve a problem? Okay? You have your equations up here. A basketball player is balancing a spinning basketball on the tip of his finger. The angular velocity, the speed of the ball, slows down from 18.5 radians per second to 14.1 radians per second. During this slowing period, the angular displacement is 85.1 radians. How long in seconds does it take for this ball to slow down? So with your neighbor, get a number. Get a number. Okay, does anyone have an answer they want to share with us? 5.22 seconds. Did anyone else get that? Good. That's the right answer. Okay? Let's solve it together. If this ball is spinning in this direction, then by right-hand rule for omega, we would have an omega vector pointing up. Now, by putting my initial omega in as 18.5 radians per second, I'm putting it in as a positive 18.5. That means I'm defining a coordinate system where up is positive and down is negative. A little bit later, the omega is still pointing up, but now it's only 14.1 radians per second. Now, during the course of this slowing down, the angle is going to go through 85.1 radians. We're looking for the time. That makes the alpha the who cares. That tells us which equation we should use. We should use the equation over there that doesn't have alpha in it. Now, before we stop caring about alpha, I just got to ask. If I did care, suppose I did, would that alpha be positive or negative? It would have to be negative because this wheel is slowing down and I'm calling my omegas positive, my alpha has to point opposite the omega. It would have to be a negative. But I don't actually, in this problem, care what alpha is. So let's find our time. The equation over there that does not have alpha in it is that second equation. So I would write delta theta is equal to 1/2 omega initial plus omega final, delta t. This is going to be 85.1. This is 1/2 times 18.5 plus 14.1, delta t, 85.1. This is going to be 32.6. Half of that is 16.3. And so delta t is going to be 85.1 over 16.3, or 5.22 seconds. Okay, see if your neighbor got that. If not, you know what to do. Okay.
That's good.
Now, in your homework, you had a problem where a wheel was spinning this way, and it had an angular acceleration of 3.76 radians per second, and it started from rest, and it went through 30 revolutions. Okay? Now that's going to be the delta theta, 30 revolutions. This problem, it has a little wrinkle, and I just want to make you aware of that, and that is that we have to have those units for angle radians. We have to have that in radians. Revolutions isn't going to cut it. So I have to change units by multiplying by the number 1. One way to write the number 1 is that there are 2 pi radians in every 1 revolution. That's going to cancel out the revolutions, and I'm going to get 60 pi radians. Okay? And then, if you're looking for the time, that makes this the who cares. And so you would use the formula that doesn't have omega final. That would be delta theta is equal to omega initial delta t plus 1/2 alpha delta t squared. This would be 60 pi. That's 0 because it starts from rest. I would have 1/2 times 3.76 delta t squared. If I solve for delta t, I get 10 seconds. And it's a very easy thing to go back and solve for omega final, which is part B. Okay? Let's move on. Suppose that you're looking down at a merry-go-round. You're looking from above like a seagull looking for a target. And what you see down there on that merry-go-round is a little red-headed kid and a little blue-headed kid. And the question is, which of those kids experiences the greatest centripetal acceleration? Now remember, centripetal acceleration, the steering wheel acceleration, is given by the formula v squared over r. And by v in that equation, we mean the tangential part of v. The part of v that's actually going in the circle. Okay? Now, the question is, which of those kids, the red-headed kid or the blue-headed kid, is experiencing the greater centripetal acceleration? So with your clicker, tell me. Okay. Let's see how we did here. Whoa, we don't know. We don't know. And folks, that's okay. Because when I write centripetal acceleration this way, it's kind of confusing. The blue-headed kid has a bigger velocity, tangential velocity, but the blue-headed kid also has a bigger radial distance, r. And one of those is trying to make that acceleration bigger, one is trying to make it smaller. So let's look at it another way. Let's use the help of, these are the Svensson brothers. They're identical quintuplets, if you'll believe it. And this fellow's name is Sven Svensson. This is his brother Sven, his other brother Sven, his other brother Sven, and Sven. Not much originality in that family. Now, they skate in a perfect line. And that means that this Sven has to skate faster than this Sven. And this Sven is just doing this. You know, he's not very talented. Now, my gut's telling me that this Sven has to skate twice as fast as that Sven, because he's twice as far from the pivot point. Let's see if we can prove that. We can prove that with the operational definition of angle in radians. If we look at what those different things mean, the S is the arc length that this Sven travels. The R is the distance that that Sven is from the pivot, and the delta theta is the angle between the line and where they started. Now here's the thing. The S is different for each Sven. The R is different for each Sven. But the theta is the same for each Sven. So if I rearrange that equation by multiplying both sides by R, and I divide both sides by time, the arc length divided by time is the tangential velocity. The angle divided by time is the omega. Here's the thing. If they're going in this line, the omega is the same for every Sven, including that one. But if someone is twice as far from the pivot, they're going to have twice the linear velocity, the tangential velocity. So we've proven that this Sven has to skate twice as fast as that Sven. Now if we go back to our little red-headed kid and blue-headed kid, and we rewrite that formula in terms of omega, well, V tangential is just R times omega. And so I plug that in for V tangential. I square everything inside the parentheses. I divide by R. And I get this formula that makes it obvious which of those kids has the bigger centripetal acceleration. The omega is the same for the red-headed kid, the blue-headed kid, and indeed every kid on that merry-go-round. But the further you are from the center, the bigger your centripetal acceleration. Now, in order to have that centripetal acceleration, there must be some net force, we call it a centripetal force, inward. In this case, it would be holding on to the bar, or the friction that's keeping them on at their feet. But mark my words, you get this thing going fast enough, that's the kid that flies off first. I know, I've got grandchildren. Oh, you're a mean guy. Okay, one more big idea before I let you go. And I'm going to introduce this with a little bit of a review. If Jeff is moving at 5 meters per second relative to this boxcar, and the boxcar is moving 30 meters per second relative to the sidewalk, Greg standing on the sidewalk thinks that Jeff is going how fast? 35. Now, what if Jeff is going 5 meters per second to the left relative to the car, and the car is going 5 meters per second to the right relative to the sidewalk? Yeah, it looks to Greg like Jeff isn't going anywhere. The car's going out from under him, but he's just right there all the time where he always was. Hold that thought. Suppose we take my old car, my Chrysler Cordoba with rich Corinthian leather, and we lift it up on this car lift that has wheels. Okay? Now, we get that thing up in the air, and it's not going anywhere, it's just sitting there. But we turn on the engine and we put it in gear and we get the wheel turning. Now turn to your neighbor and explain to them why that arrow is not only wrong, but sick and wrong. Sick and wrong. Sick and wrong.
Nailed it. No, I'm reading stories.
Okay. Vectors, no matter what they're representing, have to be straight. Vectors only give one direction, not a whole bunch of directions, just one direction. And so I have to have a straight vector, and if this were my omega vector for this wheel, what direction would it point? Into the board, into the board. Now suppose I take a piece of a blue marker and I mark a piece of rubber at the top of that wheel with blue ink. That blue ink would be moving relative to the car, if we believe what we learned with the Sten brothers, it would be moving at a tangential velocity of r omega. If I take a red marker and make a mark at the bottom of the wheel, that red mark would be moving with a tangential velocity r omega. Now, with the wheel spinning, if I were to lower that car, listen carefully to what we hear. As I get it to the ground, yeah, that's what you hear. It's kind of like when the Knight Rider comes down off his truck there. That's not what you want to hear when you're driving unless you're a 16-year-old male. Okay? Now, what you want to hear when you're going down the road is you don't want the rubber to move relative to the road. You want it always to be just nooks and crannies to nooks and crannies meshed with the road. So suppose I get behind this car while it's up, and I push on it. It's got wheels. And I get it going down the road, and I get it going fast enough so that when I lower it down, I don't hear screeching. How fast am I going to have to get that going in order to not hear screeching? Think of this example. How fast does this have to be? R omega. R omega. And that's the rolling condition. It should be called the rolling without slipping condition. But what it does, it relates the linear motion of the car down the road to the angular motion of the wheels on the car. And it's more general than that. We just showed that if we know the linear velocity of the car, we know the angular velocity of the wheels, we just have to multiply by the radius. Well, it turns out because of our operational definitions that the angular acceleration of the car, linearly, will be the angular acceleration of the wheels with this radius of the wheel. And also, if we want to know how far we get down the road, in meters per second, that's going to be how far the wheel turns times the radius. That radius is the translator, if you will, between the rotational variables for the wheel and the linear variables for the car itself. You're going to need that for a lot of problems in your homework and on the exam. Okay, have a good evening.